So welcome to this chapter of the Erlang Express course. What I'm going to talk about today is about hot code update. It's possible in Erlang to change the code that's running in a module without taking a system down. So this allows you to, this is one of the features that gives Erlang its 6 nines availability. You can change running code without taking a system down and restarting. And what I'm going to do is show you a short demonstration of how that works and then talk through the details of the technique. So I'll talk about software upgrade and I'll then say a tiny bit about the code server, which is the technology that underlies this, and the .erlang file. So let's look at an example. In fact, what I've done is I've got the example here on the board, and what we've got here is a server process. This S sets the server going. It spawns from module S, this module, the loop with no parameters, and it registers it in whatever name we want. And what we're going to do in this example is run a couple of examples and see how they have different behavior. So that's the thing that starts the server. Here's the loop of the server, and what that does is typically receives messages of a PID and a number, and it returns to that PID the number doubled. I've highlighted that in red because that's the thing we're going to change when we do software upgrade. We can also send to the running process an update message, and that calls the loop again, but in a fully qualified format, and we'll see that that has a particular effect. And finally, we've got a client code, and what this client does is send to the named process the client's PID together with an X. So this is the client that sends the message, and what it does is it simply receives a message and outputs that. So there's the piece of client code. Here's the server. Here's the thing that spawns the server. Here's the loop that forms the body of the server. Okay, and what you can see in the running example is that we've compiled that module S. So that's the first step. What we do next is we spawn two versions of that server. So we've called S:S with two arguments. The first is the Atom Server 1 and the other is the Atom Server 2. So what we have is two of those servers running with the names Server 1 and Server 2. And you can see that we've tied those particular servers to this version of the code with the blue arrows there in the graphic. Now what I'm going to do is, and you can see the effect here, I'm sending, as a client, I'm sending something to server 1, I send 1 to server 1, I get the answer 2, I do the same to server 2, I get the same answer. Now what I'm going to do is modify the code, and what I've done is I've replaced that code that said x plus x with code that now says x times x. And let's see what we do next. What I'm going to do is compile the code. You can see I've compiled the module S, and I've sent to server 1 an update message. Only server 1, not server 2. And now let's send a message to each of those servers. And what you see is that the result from server 1 is now 1. It's 1 times 1, whereas the result from server 2 is 1 plus 1 is 2. And you can see that these two servers are running the different versions of the code. You can see that from the graphic. Now let's have a look. What I've done now is modify it a second time, and this time what I do is return the value x. So the first version of the code returned x plus x, the second version returned x times x, this final version returns x. And let's see what's happening. So we've got at the moment, server 1 is running the pink code, server 2 is running the grey code. Now let's compile again and let's update server 1 again. And now what you can see what has happened here is that the grey code has disappeared. You can only have two versions of the code in the system. The newer one is the green, the older one is the pink. So now if we perform an update and we call server 2 again, we will get an error. So you can see here I've wrapped the call to server 2 inside a catch, and what we're getting is an exit there because that process has terminated because the code has disappeared. So as code disappears, it's typically the Erlang mechanism is if something no longer works, don't try and handle the failure, but just fail and let something else in the system handle that. So I think what I'll talk about next is, but I think we can see that server 1 here, server 1 is running, and server 1 is running that latest green version of the code. If we pass the argument 4, we get back the argument, the result 4. So that's returning x. It's not returning x plus x or x times x. It's returning the latest version. And you can see, you saw through this example, there were always two versions of up to two versions of the code available in the system. We started off with the grey version, then we had the grey and pink, and then we had the pink and green. So I'll talk through the mechanism for how processes update code, how the code is held within the system, and so on now. But that's a nice example that illustrates pretty much the basics of what's going on with software upgrade. So two versions of a module can be loaded in the runtime system at any one time. We've seen that, either the grey or the pink or the green. And a process can run either version. It's possible for one process to be running the old version, for another to be running the current. If the process running the old version has a fully qualified function call made to code in the module that's been upgraded, the module reference will be updated to point to the latest version. So a fully qualified function call made to any of the functions in that module will update all of them. So the update is on a module basis, not on a function basis. And you can see here we've now moved, so both versions, both of the processes there are running the current version. Now, if we have a situation where we've got a module running the old version, and we upgrade to a third version, then the module that's running version 1 will be killed, and it will crash, as we saw in the example. So there are only two versions. So even if there are modules still running the old code, they don't carry on running the old code, they are killed. So we know that the code in the system is either running the old version or the current version. It can't run any versions older than that. And the system, as I said earlier, what will happen is other things, the supervisory processes or whatever, will have to deal with that process having died, and will have to restart it or whatever. So it's important to know how code is loaded into the runtime system. If you call a function, a function from a module which is not already loaded, that will load the code for the module into the system. If you compile the module using C of module in the shell, that will load the system. Or you can explicitly, using the code module, which is a module which contains functions that perform various operations over the code, if you call the load file function from the code module, that will explicitly load the code. And just to remind you, a fully qualified function call is a call of the form module : function with the arguments, rather than simply function. So you saw here, in the example I was talking about, this is a fully qualified call to the loop L. I don't need to do that. I could, within this module, just call L at the empty with no arguments. But this fully qualified call means that if we receive the message update, we call the loop in a fully qualified form, so that will load a new version. So hence the use of the fully qualified name there and not there. So while we are receiving messages but not an update, we use the old version, but as soon as we receive an update message, we load the new. So the code server is the mechanism that handles dynamic loading of modules. And the way that the code server has a fixed mechanism for looking for compiled versions of a module. And that's using what's called the code path. And the code path is a list of directories, list of folders. And those are searched sequentially for the module that we want to load. And the first success, so it's loaded from the first place that it's found. If, again, another function for the code module is the getPath function, that will return a listing of all the directories in the path. And that includes some by default. It includes the current working directory, and it includes directories in the lib subdirectory of where Erlang is installed on your system. That's the $Erlang root variable, which says where the Erlang system is installed. Now it's possible to manipulate that path using the functions addPath A, which adds at the beginning of the list, and addPath Z, which adds at the end of the list. Again, those are functions which are in the code module. So that allows us programmatically to change what's in that list. So here's an example. If you perform the addPath A operation and then perform getPath, you can see what we get back is a list of strings, and indeed the first string in there is the C:/tools directory. And then typically you look first in the dot, which is the current directory, and then you look through the Erlang root dir. So typically you'll look for versions of a module in your current directory before you look in the libraries. So the code server can explicitly remove an old version of a module. That's called purging, and you can see that there are two purge functions in the code module. The purge will remove the old version and kill any processes which are running it, and it returns the result true if it has killed any processes. So that will, irrespective of whether processes are using it or not, will remove that old version. A soft purge will remove the old version only if no processes are running it. And that again returns true if that was a successful operation. So that allows you to remove it, but only if it's safe to do so, without killing any processes. So let's look at an example of this in practice. You can see here what we're doing is we're compiling the module S twice. So if we perform a soft purge, we get the result true. There is an old version there, but nothing is using it. Now let's run an instance of the server. Let's call it server 1. And if we perform a soft purge now, we can't. If we compile it again, then perform a soft purge, the result is false. We can't purge that code because the server is already running that code. Now we can send a message to it, and what we get back is the result we'd expect. The result we'd see from here, we get 1 + 1, so we get 2 running there. Now we can purge the code, and that's returned true because there was a process running that code. And then if we try and call that server again, we get we can see that the system has crashed because what that will do is purge all processes that are running the old code. You can see that happening there. And now if we compile again and purge, we get the result false because there are no processes running the old version of the code. Okay. Now, there's typically in your home directory, there's a .erlang file, in which you can place expressions which are executed every time the runtime system is started. And that's usable for a number of pieces of setup. You can see some examples at the bottom here. You can see an example of adding a particular directory to the beginning of the search path. You can see an example of setting a cookie, which is something that can be used in when you're using distributed Erlang. And finally, you can output a message which says, for example, that these things have been loaded. And that's the end of this section. We've seen that what we can do is, in a running system, upgrade the code for a module, and we've seen the mechanism by which new versions of the code for a module are loaded by the code loader. We've seen that you can have two versions running, an old version and a current version, but only two. So if a third version is added, the oldest is removed, and any processes running that will be killed. We've seen ways that we can handle and explicitly purge versions of the code. And we've seen that those can be done in a way that either preserves running processes or will kill processes which are running the old version of the code. But in total, this allows you to, on a large running system, selectively update whichever parts of the system you wish. And assuming that interfaces are preserved and so on, that can be done without disturbing any other part of the system. So preserving this 6 nines reliability that Erlang is famous for.